Assalamualaikum and hi everyone. So today we will present about digital filtering of audio signals, which is identification and removal of sinusoidal noise using FIR and IIR filters. So our group member is Muhammad Umar Aiman, Muhammad Izzuddin and me Muhammad Faik Iqbal. So our objective is to listen and analyze the async corrupted audio signal to identify the nature of the corruption. Examine the audio signal in the time domain frequency domain using MATLAB. Identify the corrupting signal from the FFT frequency spectrum. Design FIR and IIR digital filters to remove the corrupting signal without using the FDA toolbox. And lastly, apply bot filter, save the filter outputs, and verify noise removal through spectral analysis and listening. So for our methodology, first we're gonna do data acquisition and pre-processing, which is first we load the audio, which we use audio 22, and then we do the mono conversion. After that, we do signal properties, and lastly DC offset removal. So next, we will analyze the frequency domain and noise identification. First is we compute FFT of the raw audio vector, scale two-sided spectrum by n, which is one-sided, plot magnitude spectrum versus frequency, identify sharp high magnitude spike standing above the music spectrum.
Hi, my name is Muhammad Izzuddin. So now let's talk about with the noise identify. We design our first filter, an FIR bandstop or notch filter using the window method. We choose a Blackman window with a filter order of 600. The stop band was set from 3060 Hz to 3140 Hz, center at 3100 Hz, covering the 80 Hz bandwidth of the noise. In MATLAB, this was implemented using the FIR1 function with the stop option and the Blackman window of the length 601. The height filter order gives us a very sharp notch and excellent stop band attenuation, and importantly, the FIR structure guarantees a strictly linear phase response, which means no phase distortion is introduced to the audio signal. So our second approach was a second order IIR notch filter using direct pole zero placement. The idea here is elegant. We place a pair conjugate zero exactly on the unit circle, a target frequency omega 0, which equal 2 pi time 3100 divided by the sampling frequency zeros on the unit circle produce theoretically complete attenuation at that frequency. Control the width of the notch, we place the pole slightly inside the unit circle at a radius r of 0.9.9. The closer r is to 1, the narrower the notch. The transfer function has the numerator b equal to 1 negative 2 cos of omega 0 1, and the denominator equal to 1 negative 2r cos omega 0 r squared. In MATLAB, this is just 2 lines of code, extremely compared to the 600 order FIR, yet it achieves a theoretically infinite null at 3100 Hz. Okay, so next for this slide show at the time domain waveform of the audio at the 3 stage. The blue plot is the original corrupted audio, noisy and dense. The green plot is after FIR filtering, clean and smoother. The pink plot is after IIR filtering, also clean, similar to FIR result. Both filters successfully remove the 3100 Hz noise while keeping the original audio in.
So moving on into the results, let's look at how our design filters actually perform. Initially, our time domain plots of the corrupted audio didn't clearly reveal the noise because of the music waveform masked the interference. However, looking at our filter frequency response, we can see exactly how our designs target the problem. The 600 order FIR bandstop filter design with a Blackman window shows a sharp attenuation curve centered at exactly around 3100 Hz. Crucially, its phase response is strictly linear, which guarantees zero phase distortion across the auditable spectrum. On the other hand, our second order IIR notch filter creates an incredibly sharp theoretical infinite null at 3100 Hz using a pole radius of 0.99, though it introduces a localized non-linear phase shift right around the notch frequency. The true verification of our success comes from the frequency spectra and spectrogram comparisons. In the original frequency spectrum, you can see a massive sharp noise spike standing high above the music at 3100 Hz. This corresponds to the continuous high-pitched whistle heard in the track. Once we apply the FIR filter, that dominant spike is drastically attenuated. When we apply the second order IIR filter, the spike is completely eliminated. Looking at the spectrograms below, we distinct solid horizontal noise line running continuously at 3 kHz. In the original audio, completely disappears in both the FIR and IIR filter outputs, leaving a clean musical spectrum. So to wrap it up, let's look at the engineering trade-offs between the two methods. Our FIR filter requires an incredibly high order of 600, meaning a high computational load of 601 operations per sample and 600 delay elements. However, it provides superior audio quality due to its perfect linear phase response and unconditional stability. In stark contrast, the IIR filter achieves a deeper notch with an order of just 2. It requires minimal memory and only 5 operations per sample, making it exceptionally fast, though it is only conditionally stable and introduces minor phase distortion. In conclusion, both filters successfully restored the audio to a clean listenable state. For a high fidelity audio studio applications where phase integrity is critical, the FIR filter is preferred. However, for real-time or resource constrained embedded system, the efficiency of the IIR filter makes it the ideal choice. And thank you for watching.